Stripping down science. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Dr. Chris Smith, and with Dave Ansell.
This week we'll be hearing how earthquake science can be used to diagnose broken bones in both athletes and even racehorses, finding out how to build lasers on microchips to make them go even faster, and uncovering the cause of out-of-body experiences.
And also tonight we'll be exploring the science of catalysts, including how your car's catalytic converter works, and also how catalysts can help to solve the Earth's looming energy and pollution crises. Emma Schofield and Fraser Armstrong will be joining us to explain how that works. In this week's Kitchen Science, Dave will be doing the experiment live here in the studio, and he'll be using Emma and Fraser as the guinea pigs. If you want to take part, all you're going to need is yourself and a slice of bread.
If you fancy winning yourself a lemon-powered clock or even a copy of Dr. Chris's new book, Naked Science, keep listening to find out how.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Computer chips are starting to get a problem because they're getting faster and faster and faster, and it's hard to get information from one side of the chip to the other. So what people wanted to do is use light rather than electrical communications to move the information around. But the problem is silicon can't actually you can't make a laser out of silicon, because when you try and do it, instead of getting light out, you get heat out. You can do it with other semiconductors like gallium arsenide and indium phosphide. But the problem is that you can't even stick them onto silicon, because it's a bit like putting Lego bricks of two different... But if one Lego brick which is 50% bigger than another one on the same thing, it won't fit. So what they've done is they've worked out a way around this. If you make two very, very smooth surfaces, one of silicon, one of indium phosphide, oxidise two surfaces a bit and push them together, they'll actually stick together. This was done by John Bowers in University of California in Santa Barbara. And he's managed to get 26 of these on a chip, and hopefully it should save a lot of energy and make chips a lot faster.
Because one figure I did hear stated was that if you look at the modern-day Pentium that people are using in their computers now, the energy density of trying to force energy and electricity through the chip is equivalent to the sort of interior of a small star.
Yeah, it's about one of the most highest energy density things that anyone builds at the moment. It's scary.
So when will this be hitting the production line? When do you think this is actually going to be realistically usable?
I mean, obviously this is a research thing, so it's going to be like at least 5 or 10 years, like all these things.
Now, a honed-in athlete like yourself, Dave, could appreciate this invention, which I spotted this week. It's actually a group of scientists in the States, led by a guy called Ozan Akus, who's at Purdue University in Indiana. And what he's got is essentially a system in which he's borrowed from seismology, earthquake detection, to work out when you might be developing a stress fracture. Now, when people exercise enormously, then what can happen is the surface of bones can break, and you can get these tiny micro fractures in the bone surface. Eventually they can all add together and you get a proper fracture. But knowing when that's going to happen, and therefore when to ease back from your exercise and let the bone recover, is really hard to do, and often it's too late because athletes have already ended up injuring themselves before they actually realise there's a problem. And the same goes for racehorses. It's a major problem. So what he's done is to rig up a system, initially using bones from dead bodies, but now applying it to real-life humans. So what he's got is a piezoelectric device. So in other words, this takes tiny vibrations and converts it into electrical signals he can detect. And he's found that when bones are subject to these tiny micro stress fractures, they emit, in just the same way as the Earth does when it's having an earthquake, very high frequency sounds, ultrasound. And you can use this piezoelectric device to pick up and turn into electrical signals these tiny sound waves. And what he thinks is that just before you develop a big fracture, because all these little fractures add together, you get this very big surge in the amount of ultrasound being produced, and that kind of heralds a forthcoming fracture, and it could be used to tell people, hey, ease back on the exercise a bit.
So you're actually hearing the bone breaking, or the little bones open, or the little cracks opening and closing?
Exactly. As the bone is flexing, as you're stressing it, these tiny, tiny imperfections in the surface that are the beginnings of these stress fractures are opening up, and they're closing down, and as they're doing so with very high frequency, they're emitting this ultrasound that you can detect.
Don't the athletes notice that their bones are gently breaking?
Well, you do experience pain, but the thing is, the point that he makes is that a lot of very highly trained athletes have already got the constitution of iron anyway, and they'll put up with absolutely anything. And so, as a result, they often overdo it without realising they're overdoing it. And of course, if you've got a horse, it's not going to be able to tell you, hey, this bit, when I put weight on in this way, is causing me a bit of pain, therefore I ought to maybe have a day off. It's not till the animal goes lame that you know what to do. So in order to test this out, they actually recruited a whole group of students, and they're going to start testing it on them and seeing if they can predict in a sort of university team whether or not there's a problem forthcoming.
That should make their lives a lot more comfortable, I guess. Now, strange supernovae have been worrying cosmologists. A supernova is basically a star which explodes. There's various types of these, but the one important one is a Type 1a supernova, because these all appear to be about the same brightness, about 5 billion times as bright as the Sun. Now, cosmologists use this feature to measure how far away distant galaxies are.
But what actually is a supernova?
Well, this kind of supernova, you get a dead star ember called a white dwarf, and it's circling something big like a red giant, and it's slowly acquiring matter and stuff. It's sucking it in from the red giant, and eventually you get so much matter that it can't hold itself up anymore. They're held up by the electrons repelling each other, and eventually it gets so much gravity that it collapses. It gets very, very hot and very, very dense, and the carbon starts fusing together. All the carbon oxygen starts fusing together and making heavier elements, which is where all the heavy stuff in the universe comes from. And then it explodes incredibly violently. Now, cosmologists have used this to measure how far things are away, and from that they work out all the exciting stuff they hear about dark matter and dark energy.
Well, how can you use that to work out how far something is away?
Well, if you take a light bulb and you know how bright it is, and then it's twice as far away, it gets a quarter as bright, and you double it again, it gets another quarter as bright. So the dimmer it looks, if you know how bright it was to start with, you can work out how far away it is.
OK, here's a spanner to throw in your works, OK? If you've got a very bright star in this galaxy, and then one half as bright next door to it, but it's half as far away, how do you know whether one's further away than the other?
Well, that was what they thought was a really neat thing about these Class 1a supernovae. They're all the same brightness. The problem is a guy called Andrew Howell has found one which is twice as bright as they thought that these could possibly get.
Oh dear, so that really is a spanner in the cosmological works then?
Yeah, they're not quite sure why it is. It could be because it's spinning, so because it's spinning it will kind of stabilise it for a bit, and so it can gain more matter before it explodes. But yeah, lots of cosmologists are going to be looking very carefully at their data and working out what's happening.
So are the implications then that the universe is actually smaller, bigger, much the same as we thought it was?
We don't really know until we know how many of them there are and what's going on, basically.
So Naked Scientists, Chris and Dave, if you have any questions for us, then phone in now, 08459 25 2000. You can text in on 07786 20 1960, or you can email chris@nakedscientist.com. Now, have you ever had the feeling that you're being watched? Or, in other words, have you ever had the feeling that you're having an out-of-body experience, or the hairs on the back of your neck are standing up? You're sure there's someone standing right behind you. Or perhaps you know someone that's had, say, schizophrenia, and they've had the sensation of voices coming from outside their head, or they can see someone who no one else can see. Why is that? Well, neurologists in Switzerland this week, a guy called Olaf Blanke at the École Polytechnique in Lausanne, reckons they found the part of the brain that's responsible. And what they were doing was studying a lady who had epilepsy. And in some people who have epilepsy, because the epilepsy is so severe, it's not possible to control it using drugs. And so what you're forced to do is to go into the brain and identify the abnormal bit of brain tissue that's triggering the epilepsy. And then if you remove that bit of brain, you can stop the epileptic fits. So that's what they were going to do with this lady. So because they were doing this brain surgery, she very kindly consented to let them try some experiments on her beforehand. And what they were doing was stimulating with very low threshold electrical stimulation different areas of the brain and asking her, what are you experiencing? Because they wanted to work out what bits of the brain do what. Because if you stimulate those bits of the brain, you can very discreetly activate nerves in that area, and then you can work out what those bits of the brain actually do.
So were they actually putting wires into her head and applying electric currents?
Yes, because when you open the surface of the skull and you can see the brain surface there, that's how you're obviously going to do your neurosurgery, then at the same time you can put a tiny needle in and you can deliver a small amount of electricity just to that part of the brain, and you can recruit the nerve fibres that are there and see what they do, because it will make whatever that part of the brain does do it. And so if it's the motor part of the brain, then whichever part of the body that part of the brain is supplying will begin to move when you stimulate it. And so you can map out what bits of the brain do what. Now, they were exploring her brain, and they found a region called the temporoparietal cortex, which is where the back part of the brain meets the temporal lobe, the bit of the brain adjacent to your ear. And when they stimulated there, something very extraordinary happened, because the woman said, there's someone else in the room with me. And what she began to describe was a shadow behind her and on the opposite side of her body to the side that they were stimulating, which kind of fits because the nervous system is crossed over. Left side of my brain controls the right side of my body. Now, when they carried on stimulating this area, they found that they could get her to put herself in various positions, and this shadow person copied her position. And when they asked her to hold a card and read from it, she said that, well, this person keeps trying to take the card away from me. And what's very strange is that clearly this was a representation of her own body that she was seeing, or thinking she was seeing, and she didn't realise it was her. So this is almost identical to what people with schizophrenia get. It's almost identical to what people who have funny out-of-body experiences might get. And what the researchers think is that this bit of the brain somehow unites our sense of self and where our body is in space with consciousness. And so what they're doing is short-circuiting the part of the brain that would normally say, hey, this is you and this is where you are in space. And they were directly stimulating the bit of the brain that said, here's a representation of your body. And so she was fooled into thinking there's another one of her. And so they think this is a very worthwhile part of the brain to look at to try to understand why some people have these experiences and maybe how to tackle schizophrenia better in future.
But if she's epileptic, couldn't that be some of the reason why she's getting these strange effects?
Well, that's a very good question, and it's one that obviously that you could criticism that you could level at this study, but the thing is that until we look at more people, you won't know for sure. But the likelihood is that it's a robust finding, because the epilepsy wasn't affecting the part of the brain that they were stimulating. That part was, as far as we know, normal. So probably, until we check, obviously, with another person, you have to say, we'll take it with a pinch of salt, but because this was a paper in the journal Nature this week, which is one of the best science journals, I think I'm inclined to believe it.
Cool.
If you'd like to drop us any questions here on The Naked Scientists, 08459 25 2000, email chris@nakedscientist.com or text in on 07786 20 1960. In 2 ticks, Dave's going to be telling you how you can turn your body into your own experiment. We're looking at catalysts this evening, and in particular enzymes. So we're going to need a bit of bread, so get yourself a slice of bread, and either yourself or a willing volunteer.
The Naked Scientists, supported by the Wellcome Trust.
For this week's Kitchen Science is incredibly easy. All you need is a piece of white bread, as cheap and boring as possible. Economy value is the best you can get. Brown bread does work, but it's a lot harder to tell what's going on. And a mouth of someone with a little bit of self-control.
What's that supposed to mean?
Well, I'll get to that in a minute. All you have to do is take about half a slice of the bread and chew it a bit more, keep chewing it even though it's getting disgusting, and then chew it a bit more. And all you got to do is, while you're doing it, try and work out what happens to the taste. You need the self-control, because chewing a piece of bread for that long is actually really quite difficult.
So they mustn't swallow?
You mustn't swallow, just chew it and see what happens to the taste.
And it's the taste that people are concentrating and focusing on?
That's right, yeah. And if they can phone in and tell us what happens and they get it right, there's a chance of winning a prize.
So what you want to know is what happens to the taste, and for a bonus mark, why?
Sounds about right to me.
OK, well, that's one way in which you can win tonight. And we've got some great prizes, because here in the studio with us, we have Emma Schofield from Johnson Matthey Technology Centre in Reading, and also Professor Fraser Armstrong from the University of Oxford. And they're going to later on be talking about catalysts and how the catalytic converter on your car works, for instance, and also how we can make cheap hydrogen fuel, which might solve some of our energy and pollution crises that the Earth could be facing in future. So if you've got any questions for them, give us a buzz, 08459 25 2000, or alternatively, you can text in on 07786 20 1960 or email chris@nakedscientist.com. But we've also got our weekly teaser. This is where you just phone in if you think you know the answer to tonight's question. We want to know what gas makes up the majority of the air that we breathe. Do you know the answer? Call now if you reckon you've got an idea.
Laying the facts bare, The Naked Scientists.
Time now to take our regular trip over the Atlantic to hear what Chelsea and Bob have got for us on this week's Science Update. This week they're taking a look at the record breakers of the science world, which includes the world's fastest moving body part, and also, ouch, the sharpest needle on the planet.
This week on Science Update, we'll talk about some ants that have set the world record for fastest moving body part. But first, Chelsea reports on another world record for sharpest object.
The tip of the world's sharpest needle is a single atom of tungsten. I asked physicist Bob Woolcoe of the University of Alberta what it would be like to hold it in my hand.
It would be just like a sewing needle or a pin. You would see that it was very sharp, but you wouldn't be able to see the end of it. It's so small it's invisible. And if you put it under the most powerful microscope in the world, you would only then just barely see the tip of it.
Woolcoe says they make these needles by exposing a normal needle made of tungsten to nitrogen gas and electricity. The gas and electricity interact with the end of the needle to pluck off atoms until there's only one left.
It's kind of like sculpting. In a sculpture, the final shape is already in the block of stone, and the sculptor knows what to take away. Well, we're not sculptors, but where we take away the atoms from the edge, leaving behind a tiny, tiny needle.
Since it's so sharp, Woolco says the needle could prove to be the best probe ever made for use in powerful electron microscopes.
Thanks, Chelsea. A type of insect called the trap-jaw ant has jaws that now hold the record for the fastest-moving self-propelled body part in the animal kingdom. Well, that's pretty cool, but it's what they do with those super-speed jaws that's really interesting, according to University of Illinois entomologist Andy Suarez.
These ants will use their mandibles not only to capture food, but to propel themselves off the ground to escape threat or predator.
Using a high-speed imaging system, Suarez found that the ants cock their jaws open against the ground and then snap them shut at close to 100 miles an hour. That's enough force for some pretty impressive flips and serious hang time.
In the field, when they start jumping around, it's just a fraction of a second. They just pop up in the air and they're on the ground again. And when you can slow this down and kind of dissect the movement and kinematics of what's going on, it's really quite beautiful. It's very acrobatic.
Suarez says the ants probably first evolved the fast jaws to capture prey, but then repurposed the skill to escape becoming prey.
Thanks, Bob. That's all for this week. Next week, we'll discuss a new estimate of how many types of dinosaurs are still waiting to be dug up. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks, Bob. And as always, if you want to hear a bit more from the Science Update crew, including unfeasibly sharp needles, then you can go and have a look at their website, which is www.scienceupdate.com. Now, Dave, I'm chomping away on my bit of bread here, doing your experiment, and I have finally cleared it from my mouth, just enough to be able to speak. I've got a question for you. This is from Adamski. He emailed this in and says... I'm afraid I'm just a UK listener, not like the usual folk from the international corners of the world, so he gets a mark for wit there. Something's been bugging me. On a recent trip to Sweden, I noticed at the check-in desk that my mobile battery was running low and was just about to turn off. As I went through airport security, my mobile was sent through the X-ray machine. Lo and behold, when I next looked at the phone, there was almost a full charge. I was wondering if you have any ideas why this could be so. What do you think?
There's a couple of reasons why it could be, but it's unlikely it's anything to do with the X-ray machine itself. More to do with it being turned off. One thing is, if it was quite cold when you went into the airport, batteries are a chemical reaction going on inside, and so when they get cold, the chemical reaction slows down, which means that they can't produce as much current, so the battery will appear to be a lot emptier than it is. So sometimes if you've got a flat battery on a very cold day, once I went to Russia, my camera batteries wouldn't work at all because it's like minus 15 outside. The other thing it could be is if you have a battery and you've been using it a lot, you sort of drain all of the... it'll drain quickly, and the voltage will go down. If you turn it off, that voltage will slowly build up, as long as you're not drawing a current. So when he turns it back on, it will seem full, even though it's actually no fuller.
Thanks for that, Dave. In fact, I would think, it's a sort of chemical equation going on. And, since the chemical equation wants to move from one substance reacting with another substance to produce some electricity in another substance, all the time that you're putting lots and lots of load on the battery by using it, then when those substances that are reacting together begin to run down a bit, then obviously there's a limit to how fast it can produce the electricity. But if you turn it off for a while, then you can reaccumulate those substances ready to react, and then you get a bit of a surge when you turn it back on. Yeah,
and it'll go flat very quickly. I've got a question here for you, Chris.
Oh, good. Let's see. Let's do it.
Is a question from Richard Brassington, and he has a question about cells. He's homeschooling his son, and they've been studying cell division. The textbook says that specialised cells, e.g. muscle cells, don't divide. Why?
That's actually a very good question, and it's the question that's frustrating cell biologists and stem cell biologists and people who want to repair the human body. It's exactly the same reason why, if you have a stroke, part of your brain gets damaged forever and it doesn't really recover very well. It's the same reason that if you have a heart attack, the part of the heart that's affected by a heart attack, the muscle dies and doesn't recover, doesn't regenerate, because what cells have done, when they've turned from the single fertilised cell that's the egg that gave rise to you when it's fertilised and turned into an embryo, what those cells do is to specialise, and as they divide and turn into different tissues, they specialise and subspecialise. And it's a bit like when you first go into medical school, let's say, you can become any kind of doctor, but after you go through training and you go through a bit more training, you might become a surgeon. And then you don't really do much medicine, you just do surgery, you chop things out of people. The next thing you do is you become a specialist in, say, vascular surgery. You're only good at chopping out blood vessels, you can't do anything else. then you become so good at doing that, you only do surgery on people's aneurysms, arteries that have blown up too big. And you therefore wouldn't want to go and do brain surgery because you're no good at that. So that's the kind of specialisation that happens as we develop. And so the tissues that we have in our body are full of specialised cells that just do one particular job. And that means they've turned off the genes that make them a general cell, and they lock on to being one particular kind of cell. And that's a process referred to as differentiation. And it seems to be, in some tissues, a sort of irreversible step. But now people are beginning to realise that it might be possible to persuade cells to go back the other way with the right environment. If you give them the right kind of growth factors, you can make them de-differentiate and become less specialised, and then they can retrain as another kind of doctor, if you like. Or you can go back a step and you go to the stem cell, and that's like your medical student that can turn into almost any kind of doctor again. So that's why cells don't naturally turn into other kinds of cells again. Once they've differentiated, they can become lifelong cells. The cells in the brain last a lifetime. Some cells in muscles can last a lifetime, although there are some stem cells in there that can regenerate them. And some other tissues in the body have cells that have to last you a lifetime, and if you destroy them, they can't be replaced. I've got another one here for you, Dave. And this was interesting. This is from Graham Watson, who is at University College in London. He says, I was walking along St Martin's Lane, Gower Street, to University College, where I work for Cancer Research Technology, and I listened to your podcast as I make that walk. It makes it much more interesting. But here's an interesting observation. Take a helium balloon and hold it on a piece of string inside a car. Watch what happens to the balloon when the car brakes. It moves backwards, so it goes the opposite way to the rest of the objects in the car. So in other words, if you did an emergency stop, you might hit your head on the dashboard or whatever, but the balloon goes the opposite way. He says, what's happening here?
Well, this is because basically when you do an emergency stop, the car is accelerating everything in it backwards, or the wheels on the car are accelerating everything backwards. And so everything relative to the car rushes forwards. Now, in the air, basically the balloon is floating in the air. But if it's a helium balloon, the air is heavier than the balloon itself. So the air is going to want to rush forward more than the helium balloon is going to want to rush forward. So the air is going to push the helium balloon out of the way and push it backwards. And the same thing would happen if you had, a boat on water, boat sort of dragged underwater, and you slammed your foot on the brake hard.
If you could in a boat, so to speak.
Well, it's more if you had a boat in a tank of water in your car,
yeah,
then the boat would float backwards as opposed to forwards. Would this have, because does this have anything to do with brains? Because Richard Hammond had a horrible accident recently, had all sorts of strange brain injuries, not necessarily at the front of his head.
Yeah, that's good. There is a brain problem. When you have a head injury, say you stop in your car very fast and your head hits the dashboard of the steering wheel, obviously the brain is bobbing around in fluid called cerebrospinal fluid inside your skull, which means that after your skull stops, the brain carries on travelling for a short while afterwards and then cannons into the front of your skull on the inside. That can put a bruise on the surface of the brain closest to the front of the head. But then it rebounds and goes back the other way, and then the back of your brain hits the back of your skull as a sort of bouncing effect, and you get what's known as a contre-coup injury, and you can get a bruise there as well. So you get people who, although they've only got a head injury in one place on their head, can actually have a bruise on their brain in two places. Obviously, I don't know if that's what's happened to Richard Hammond, but it's certainly possible that if you have this deceleration trauma, then that could be an issue.
So not really the same as a helium balloon, more just a bouncy ball but rattling around inside your head.
Yeah, it's interesting, because if you look at woodpeckers, you'd think that they would be subject to this kind of damage, because people in the 1970s decided to work out why woodpeckers don't get brain injuries when they hammer into trees, because they set up a really fast camera that could take thousands of pictures a second, in fact, and they worked out that the woodpecker's head hits the tree when it's hammering into a tree with 1,200 times the force of gravity. So that's a pretty serious deceleration. When you think a racing driver going around a bend in a very fast car might experience at 3G, 3 times the force of gravity, and that feels pretty bad, doesn't it? Like a fairground round, 3G. Woodpecker, 1,200G. Why doesn't its brain disintegrate? So they looked into it quite carefully, and part of it is that its brain is quite tightly held inside the skull, so it doesn't have this brain bobbing around to get these contre-coup type injuries. Another adaptation it's got is the brain is very smooth on its surface. It's not like a cauliflower, like the human brain. So the force of the impact is spread over a very big area of brain tissue, not just concentrated on one little bobble of brain tissue. So that's a benefit too. And also, there's another impact getting head injuries, and that is that when your brain is in an injury like this, the brain isn't just a homogeneous mass. It's not the same right the way through. Some bits of it weigh more than others. And this means that some bits stop after others, or they try to carry on for longer than others. And this is the sort of process of inertia. And what can happen is that if you have a sudden deceleration injury like that, then your different bits of your brain can sort of twist themselves off each other, rather like a lid coming off a jar. And this can tear nerve fibres, and it's called a rotational injury. And what woodpeckers do to minimise that is that they line their head up absolutely dead set on with what they're going to fire into, and they do a couple of test taps first to make sure they're dead in line, and then they don't have any of that rotational injury.
There you are.
So anyway, it's The Naked Scientists, Dave and Chris, and if you want to have any questions this evening, we'll answer them for you. 08459 25 2000, text in on 07786 20 1960, or email chris@nakedscientist.com. We've got a teaser this evening, which is what gas makes up the majority of the air we breathe. Up for grabs, we've got a fantastic prize, which has been donated by the guys at Noise. More about that coming up shortly. It's a lemon-powered clock, since we're talking about clean energy. A lemon-powered clock up for grabs. And also, if I have any spectacular questions, I'll give you a copy of my new book, which is Naked Science. We've heard a few people having a go at our quiz this evening. Anne's in Cambridge. She reckons the answer's carbon dioxide. Not quite right, Anne. John in Warrington thinks it's carbon monoxide. I'm glad I don't live in John's world. Andy on the A120 is on the right lines. If you think you know the answer, give us a call now, 08459 25 2000.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
It's The Naked Scientists, Chris and Dave, and this week we're exploring the science of catalysis, in other words, catalysts, and how the catalytic converter on the exhaust pipe of your car works. And to help us do that, in a second we'll be talking to Professor Fraser Armstrong from the University of Oxford. But first, here's Emma Schofield from the Johnson Matthey Technology Centre in Reading. Hello, Emma.
Hi.
Thank you for coming along and talking to us. So, first of all, everyone uses the word catalytic converter, but what is a catalyst? Why is it important?
A catalyst is a substance which makes a chemical reaction happen more easily. You can get some really stroppy reactions which you want to rearrange the atoms in them to make something which is useful, but it's just not playing. The starting material that you begin with is just not interested in turning into the product that you want. If you put the right catalyst into this reaction, you can make this reaction either happen more quickly or using a lot less energy, because often you have to go to high temperatures and high pressures to get the reaction to work.
How do they do that?
Well, imagine that you've got yourself a beach cottage down in Cornwall somewhere, and the beach is about a mile away from your cottage. Okay, now, between you and the beach, there is this massive great mountain, and you have several options for reaching the beach. One of them is that you put lots of energy into it, so you have to climb all the way up the mountain and down the other side. Not great. The second option is that you walk all the way around the mountain, which takes a heck of a long time. But if somebody's actually gone through and dug a tunnel from one side to the other, you can get to the beach very quickly and with a lot less energy. And this is exactly what a catalyst does. So the catalyst does for a chemical reaction what this tunnel does for you. It gives an alternative pathway that allows this reaction to happen a lot more easily.
And just like a tunnel, then that chemical is not being used up in the reaction, so it's sort of continuously available forever, if you like.
Yeah, and that's why you only need a tiny amount of the catalyst when you've got a chemical reaction, because it may get changed in the reaction, but then it's regenerated at the end of it. So each little atom or each little molecule of catalyst that's in there can go on and react with hundreds and thousands of millions of reactant molecules.
It sounds fantastic, but how do we find these things?
How do we find
catalysts? Why haven't we got a catalyst for everything? Why isn't there a catalyst for my homework, for example, when I'm at school? Or how do we actually discover the chemicals that actually do these clever jobs?
There's quite a lot of metals which are used in catalysts, because there are two different types of catalysts. There are homogeneous catalysts and heterogeneous. In homogeneous catalysts, the reactants and the products are in the same phase, so if it's two gases reacting, the catalyst will be a gas as well. In a heterogeneous reaction, the reagents are in a different phase from the catalyst. So an example of homogeneous would be making plastic bags, high-density polyethylene. The ethene and the catalyst are both in the same phase as the reaction. It's all going on in solution. That would be a homogeneous catalyst. In a heterogeneous catalyst, that would be, for example, carbon monoxide turning into carbon dioxide, and that would happen on platinum metal. And because
they've got expensive tastes, these things, haven't they?
Platinum is very expensive, but you often find that some of the most expensive metals are the ones that turn into the best catalysts.
Why is platinum, apart from being extremely nice for wedding rings and very expensive, but why should that make it a good catalyst? What's special about the metal? How does it do what it does?
When people ask questions like this, scientists' usual answer is, oh, well, it's quantum. Actually, it's to do with how well these gas molecules can stick to the surface. So platinum is very good at sticking molecules onto the surface of it. That's very important because that's where the reaction actually happens. The other thing that platinum is good for is, well, when you have a molecule, the atoms in the molecule are stuck together with chemical bonds, which are electrons. Platinum is very good at rearranging these electrons and allowing the molecules to turn into something else, again, forming this alternative pathway by which a catalytic reaction can happen.
So if you could zoom in on the platinum surface, what would it look like to make it so sticky, so that things like it?
It would look... We always imagine it as lots of little balls stuck next to each other, and one of the aims of being a catalyst chemist, which is what I am, is to try and make as much surface as possible. So we have our tiny little pieces of platinum, which are stuck on a kind of ceramic support, which and we want as much platinum on the surface and as little platinum in the middle of these balls as possible. The platinum is part of the periodic table, which has lots of d orbitals, and it's these magic d orbitals, which is, again, we're going back to the quantum side of this, that makes it so good at doing catalysis and making things stick to it. So it very easily forms bonds with lots of different types of molecules.
And then brings them together in just the right way that they want to get married or do whatever you want them to do.
And provides a route which gives them enough and which requires so little energy that it can happen essentially spontaneously or with very little energy on the metal surface.
All right, well, turning to what comes out of your exhaust pipe, you know, how does a catalytic converter on a car actually work? What's it doing?
Well, the catalyst on a catalytic converter is essentially a can which is next to the engine. And what it does is it purifies the exhaust gases, because the gases that come out of the engine, if it was ideal, we would just get carbon dioxide and water out when fuel was burnt in an engine.
I think some people would argue if it was ideal, we'd just get water, because we'd be burning hydrogen, which is what Fraser's going to talk to us about later, isn't it? But
problem being is that we put fuel in the beginning, and fuel has carbon in, and you can't destroy the atoms as you go along. But what we also get out is carbon monoxide, which is a poison that will bind so strongly to the blood that you can't bind oxygen anymore. What's called NOx gases, which are oxides of nitrogen, which are responsible for acid rain. Hydrocarbons, which come together with NOx to form smog. And this is why in the 1970s, Los Angeles essentially got buried under this huge cloud of photochemical smog. And that was what triggered all of the legislation about car pollutants. Also, what comes out is particulates, which is essentially soot, and this is linked with respiratory illnesses as well as cancer. So we obviously don't want these coming out of the back of our cars. So we need to put the catalytic converter between the engine and the exhaust pipe to catch these things as they go out. So inside the catalytic converter, we have the monolith and the metal. Now, the monolith is a ceramic, like the ceramic which is in the tiles in your bathroom. And it's a honeycomb, very, very large surface area, which is coated to give it an even greater surface area. And actually, if you spread out the area of this monolith, it would cover about 3 football pitches. Now, on the channels of this monolith, you have little globules of the metal, platinum, palladium, rhodium, various different mixtures depending on whether you're petrol or diesel car. And these are so small that we call them nanoparticles. Now, this is what we were talking about before. As these gases go past, which is very, very quick reaction, the gases out of the engine go through the catalytic converter in less than 1/10 of a second.
So it must be very, very fast.
It's a very fast reaction, and it would never happen normally in a car if you didn't have that catalyst there.
So how much of the gases does the catalytic converter scavenge or convert? Does it do the lot?
It causes about a 90% decrease in the amount of pollution coming out, and what you mostly get out of the other end is nitrogen, water and carbon dioxide.
So it does a good job. There was a motivation to stop people using leaded fuel because everyone said it makes your brain rot and it causes dementia, but also it's quite poisonous to catalysts, isn't it, the lead in fuel?
Exactly. If you think about these little metal particles, the lead will stick on the surface of the particles. The more that you reduce the amount of surface there is, the less chance these pollutant gases have of sticking to the surface and making the catalyst catalyse.
So it's better to do without lead if we can, for more reason than one.
It's better to do without lead, and it's also better to do without sulphur in petrol, because sulphur is responsible, or used to be responsible when we had high sulphur petrol, for this eggy smell that some people sometimes associate with catalytic converters. Now there's less sulphur in fuel. This is much less of a problem.
Now, Emma, it's impossible to miss your T-shirt, and on the subject of noisy engines, I wondered if that was what you were talking about to start with, but it actually says noise. Tell us what actually is noise and why you're here today.
Noise is the New Outlooks in Science and Engineering campaign, and it's a group of young scientists who are there to come up with an alternative image for what scientists are like. So, I mean, Chris, when you think about the stereotype of a scientist, what is it that springs to mind?
Glass is more powerful than the Hubble Space Telescope. Shocking teeth, 1960s get up, muttering unintelligibly in a language no one can understand.
Right, and this is, I mean, the words fun and dynamic don't really feature in the kind of descriptions.
But that's why people listen to The Naked Scientists.
Well, that's why noise is there, because we need to change this. We're the new generation of young scientists, and we have a website, noisemakers.org.uk, where there's this whole group of scientists who do lots of fun science which we want to tell people about. We have a snowboarding physicist, we have somebody who does robotics, who is a scuba diver, and the idea is essentially to point out to people, particularly kids who are thinking of going to university, that there is more to a scientist than a white coat.
OK, well, that's Emma Schofield, who's from the Johnson Matthey Technology Centre in Reading. She's here if you'd like to ask her any questions. The phone number's 08459 25 2000. You can text her on 07786 20 1960 or email chris@nakedscientist.com. In a second, we'll be talking to Professor Fraser Armstrong from the University of Oxford about how we can make cleaner fuels, particularly fuels structured around hydrogen. Our teaser this evening is also on the subject of gases. We want to know what gas makes up the majority of the air that we breathe. We've heard from Keith in Peterborough, Brian in Suffolk, John in Peterborough also, Jerry's in Northampton, Norma in West Runton, Ruth's in Hoston, and they all have got the answer correct. Up for grabs this evening is a lemon-powered clock. We're talking about clean fuels, and there's one for you. I'll also give you a copy, if you've got a good one, a good question of my book, Naked Science.
Stripping down science.
OK, let's do it.
The Naked Scientists.
OK, with us this evening we've got Fraser Armstrong from Oxford University. Now, you work on fuel cells. Can you start by explaining what a hydrogen fuel cell is?
Well, first of all, hydrogen is an energy carrier, much like petrol is, or any sort of oil or coal. But, of course, it's a very different type of energy carrier because it's a gas. And it's not necessarily a very convenient energy carrier because, of course, hydrogen is a gas all the way down to about plus 20 Kelvin. That's about minus 250 degrees Celsius. And so it's not a very convenient fuel. But when combined with oxygen, as most of us remember from school, even doing that experiment still in school, hydrogen and oxygen make a bang together and give off water.
People on the Hindenburg knew a bit about that, didn't they?
Well, they did, unfortunately, yes. But hydrogen is a very good and light fuel. That's why it's used in spacecrafts, even if it's not very useful in terms of being able to transport it efficiently.
Just as an aside on that Hindenburg thing, it's actually a bit of a myth that it was all the hydrogen blowing up, although that didn't help, because when the Germans built that, they thought it looked nice as a silver colour because it showed their Nazi swastika very, very nicely. And in order to get that silver colour, they sprayed it with aluminium, and the tiny aluminium particles burned beautifully.
A bad choice of
it was a very bad choice. Sorry, Dave, I didn't mean to interrupt.
So what does an actual fuel cell look like?
Well, a fuel cell consists of two electrodes, one on which hydrogen is oxidised to protons, and of course, as we've just heard from Emma, this involves a catalyst, and the catalyst in this particular case is generally platinum, or platinum with other precious metals. Hydrogen is oxidised to protons, and at the other electrode, oxygen is reduced to oxide. Now, the oxide and the protons combine to form water, and we find that we have a large amount of energy produced from this, which is the same amount of energy as would be produced if we actually deliberately burnt hydrogen and oxygen and got an explosion. But now the energy is converted directly into electricity, which can be used to power devices.
So I guess there's a problem if the hydrogen gets on the wrong side and the oxygen gets on the wrong side. How do you normally solve that problem?
Well, generally, these are the anode and the cathode, as the two electrodes are called, are separated by a membrane called the proton exchange membrane, and hydrogen is directed at one of the electrodes and air is directed at the other electrode. And generally, there's very little in the way of what is called crossover, which is the mixing of gases.
Since this show is about catalysts, I've got to ask, what is the catalyst that's doing this in your fuel cells?
In the conventional fuel cell, which is called a proton exchange membrane fuel cell, the catalyst is platinum, as we heard from Emma. My research group is investigating the possibility of other types of catalysts for this type of technology, particularly ones which are based on enzymes which occur in microbes. And these particular enzymes do not, of course, contain platinum as their active centre, but they contain other elements which are much more familiar to us, in particular iron and most often nickel as well.
I guess this is a big advantage because if you powered all the cars with platinum, with platinum fuel cells, you'd run out of platinum quite quickly.
Well, either we'd run out or the price would go up and up, there's always a good point in having alternatives to the catalysts which are on the market.
So why do we need, why do bacteria need to be able to do this with hydrogen? What's the point of that?
Well, very interestingly, the bacteria have used hydrogen as a fuel for over 2.5 billion years. If we go back in time to the earliest life forms, at that particular time there was no oxygen on the Earth, and many microbes would use the proton as an oxidant. And of course, when one reduces a proton, we obtain hydrogen. And so many bacteria have the ability to make hydrogen from protons, that is, from water. And equally, other bacteria have the ability to use hydrogen as a fuel. So there's a type of cycling which is possible in the microbial world.
Is it possible for us to co-opt this efficiently enough to run our cars, though?
No, I don't see this running. I don't see this ever running cars because, as it stands at the moment, the problem with enzymes is that they're not designed to last forever, and they're not designed to withstand very high temperatures and very high reaction conditions. However, we can learn a considerable amount from studying the active sites of the enzymes, that's the molecular structure of the enzymes. In other words,
the part of the enzyme that's the business end that does the catalysis. The business end
at which catalysis occurs, yes.
And what, you'd hope to make a model of that or to reproduce that more stably?
Either for the purposes of high energy or high power purposes, it may be possible in the future to make catalysts which are alternatives to platinum, which use the chemistry of the active sites of enzymes as we currently understand them. It may also be possible to actually use enzymes themselves for power production, which is much less demanding than the automotive industry.
So the advantage of your new fuel, your design with the enzymes, is that you don't have to keep the hydrogen and oxygen separate anymore.
In principle, that may not be that may be quite correct. It is possible to mix hydrogen and oxygen to get non-explosive mixtures. However, the amount of hydrogen that one requires for this is less than 4% in air, in order to avoid hazardous mixtures.
Got a quick question for you, Emma. Andy's on the A120, wants to know about cars smelling like rotten eggs after a long drive. That's down to a catalytic converter, isn't it?
It's not exactly a myth, but it's something that's becoming less of an issue nowadays. The reason that happens is that there is sulphur in fuel, and when the sulphur burns in oxygen, it forms sulphur dioxide. Now, this only really happens in a petrol engine, which can operate under fuel-rich and also fuel-lean conditions. Now, in fuel-lean conditions, there's quite a lot of oxygen, so the sulphur in the fuel gets oxidised to sulphates. This is a real pain because this clogs up the catalyst and builds up on the surface of the monolith. But when you start a car, that's the point at which you have fuel-rich conditions. Now, this is going to convert the sulphate, which is built up on the catalyst, into H2S, which is hydrogen sulfide. And that's the kind of eggy smell that you get out. But this is why we're getting a lot more low-sulphur fuels nowadays. And to be honest, it's a lot less of a problem than it used to be.
OK, we've got another question on email here for probably Fraser. It's a question from Peter Han. He's asking why compressed natural gas, or methane, burns cleaner than regular fuel. It's still a hydrocarbon. Why shouldn't it combust in the same pollutants as everything else?
Well, there's really two sides of this, and that is the amount of carbon monoxide, that's what we call CO instead of CO2, carbon dioxide, and also the amount of soot, which is much more close to pure carbon. The amount which is formed depends on the carbon to oxygen ratio in the mixture, so that coal, for example, and many long-chain hydrocarbons have a much higher carbon content, so it's necessary to have very much higher oxygen content in the mixture in order to avoid the formation of what we would call lower oxides or soot.
So basically, if you've got lots of carbon there, it's very easy to get something slightly wrong and not completely.
That's right. There's
things.
not enough oxygen to take it all the way to CO2.
It's the Naked Scientists, Chris and Dave, and we're talking this evening with Emma and Fraser. And if you want to ask us any questions, 08459 25 2000. Lots of people having a go at my teaser this evening, which is what gas makes up the majority of the air that we breathe. I've heard from Gio, who's in Cambridge. Also, Steve's in London. He's got the answer right, as has Karen Bamford in Essex. Now, Karen also goes on to say she's got a catalytic dilemma. Perhaps you can help her, Emma. I don't know. She says... she also points out that she's jokingly been through all the possibilities for the gas question, including oxygen and possibly methane, which she says is the highest in her house. Sounds nasty. She says, really enjoying the programme. Like to know if it's possible to change your hair colour without chemicals, perhaps by gene modification or something like that. It would save her a fortune. But actually, are there any catalysts on the market that could catalyse a platinum blonde colour or perhaps a red colour or something?
Well, the chemical which you normally dye or bleach your hair with is hydrogen peroxide. Now, interestingly, that's a typical catalytic reaction which you do in school. Hydrogen peroxide decomposes into oxygen very, very slowly. But if you add, for example, potassium iodide, you can make this happen a lot more quickly. And there's a fantastic experiment you can do where you put some hydrogen peroxide...
A contact lens fluid.
Yeah, something like that, or hair dye, whatever you can get hold of, and add a little bit of potassium iodide and some bubbles, and the whole thing comes sweeping out of the top in this great fountain of bubbles. So...
you can do this exciting thing with carrot as well, and blood, although I wouldn't advocate pricking your finger, but if you prick your finger and put some contact lens fluid, put it on a surface and put some contact lens fluid, blood has got the enzyme catalase in huge amounts and it will fizz up like there's no tomorrow, and so will carrot. Carrot's got loads of catalase and it breaks down hydrogen peroxide and makes, of course, oxygen, so...
But as for trying to dye your hair without a catalyst, I would go the catalyst by myself.
Let's have a quick chat to Pom, who's in Kent. Hi, Pom.
Hi.
Hi, thanks for joining us. Welcome to the programme. What can we do for you?
Yes. I was just curious about this scaremongering we hear about the ice caps melting and causing widespread flooding to come.
Yep.
When I thought the principle, the Archimedes principle, was that a body immersed in water, and given that the majority of the icebergs are in water, obviously there's some on land.
Yep.
When the ice melts,
yep,
it will only displace its own weight in water. In other words, if you put a chunk of ice in a glass or a cup,
and
then fill that up more or less to the top with water, the ice would stick up above it.
Yes.
And it would melt, but it wouldn't overflow the cup.
Yeah, I understand the point you're making, and it's a good one, and you're half right and half not right.
Well,
and the reason is as follows, that the North Pole is ice that's already floating.
Yeah.
So if that melts, quite right, just like your glass with ice in it, when the ice melts, it's never going to overflow because the ice is made of water and it will displace an equal weight of water as itself, and since it's made of water, it will just turn into water, and so it will never overflow. But here's the spanner in the works.
Yep.
Greenland, for example, and Antarctica are continents. There's land under there and the ice is not in the water, the ice is sitting on land. And if that melts, then it's going to raise sea level drastically. And in fact, there's enough ice locked up in Antarctica and Greenland to give us about 7 to 70 metres of sea level rise. And in fact, there's a paper which was published in this week's edition of the journal Nature. It's a couple of scientists in the US, and what they've done is to use 2 satellites in space. And the satellite's actually called GRACE, but it should be renamed BRACE because they work in concert, these 2 satellites. And they work out how much mass there is on Earth underneath them by working out how fast one is accelerating because of gravity compared with the other one. And what they've done is to watch Greenland for the last 2 years, and they've found that Greenland has lost 248 cubic kilometres, plus or minus about 60, cubic kilometres of water in every single year in the last 2 to 4 years. And it's gone up 250%. So it's a scary amount. That is enough to raise, every single year, sea levels by about 0.5 millimetres. Just Greenland on its own in 1 year. It's a huge amount. So if things really do take off with global warming, we're all in trouble.
Well, as I live on the banks of the Medway.
Not a good choice.
And I'll be swimming soon.
We're going to have to move on because we've got to catch up with what's happening on the roads, okay? But it's a great question. Look, I like it. I'm going to give you a copy of my book.
Can I give you the answer to the teaser?
Tell Petro, because I don't want to give the game away until just the right time.
Yeah. Okay.
All right, then.
I'll do that.
Take care now.
Bye.
Ta-da.
Sorting out the sparks from the quarks. The Naked Scientists.
And here we are with Naked Scientists with Dave and Chris. Now, you may have remembered earlier we asked you to do a kitchen science experiment. All it involved doing was chewing some white bread. We have our two guests over here who've been chewing away. Have you noticed anything happening to the flavour of that bread?
Fraser, through the mouthful.
This bread tastes absolutely disgusting.
Dave, what have you done with it?
Well, you may have noticed it slowly gets sweet as you chew it.
It's starting to get sweeter, yeah.
Just starting to get
Okay, well, let's see if Daniel, who's on the line, agrees. Hi, Daniel.
Hello?
So you've had a go at our kitchen science?
Yeah.
So these guys in the studio, we've got our two guests have got a very... well, they've got mouthfuls of this disgusting bread that Dave's given them. What did you find when you chewed your bread?
It goes all pulpy like porridge and sticky.
Did you notice it tasted any different?
Yeah, it tastes like wheat.
Tastes a bit like wheat. Do you notice getting any sweeter?
It got a bit sweeter.
Yeah, the kind of the liquid which comes out of it is a little bit sweet.
Yeah.
Okay, the reason why that's happening is that bread's made up of something called starch. Now, starch is made by plants and wheat, because plants, they take in sunlight and they make sugar out of it. But they want to store lots of energy. They want to store all this sugar in their leaves and in the cells and things. The problem is, if you put lots and lots of sugar in a cell, it acts a bit like putting salt onto a slug. It will cause the rest of the plant all the water gets sucked out of the rest of the plant into that cell and cause the cell to explode. Now, that's a bit of a pain if you're a plant. So what they do is they take all the little sugar molecules and they glue them together into a great big long chain, which we call starch. It doesn't have the same effect, so the cells don't explode. Now, starch is a great food. It's in potatoes and especially white bread, and we eat it. But the problem is we can't absorb it into our body as these great big long chains. We've got to cut it up. So what happens is there's actually a catalyst in our spit called amylase, which cuts up the big long chains back into sugar molecules. So as you chew it gently, you get a sugar called glucose release, and it's slow and it goes really sweet and it tastes really horrible. So that's why when you chew bread, it gets sweet.
Does that enlighten you, Daniel?
Yeah.
Hey, thank you for having a go at the experiment. I'll tell you what I'm going to do, because you actually did the experiment and you were first through with the observation. I'll give you a copy of my book, OK?
Okay.
Well done.
Hey.
All right, thanks for joining us on The Naked Scientists.
Okay.
Dave, why do we need this enzyme in our spit?
Well, basically, your cell wall, your stomach wall is fairly solid, and it's only got very, very small holes in it. And so, in order to absorb sugar through it, you've got to absorb food through it. You've got to break the food up into really small molecules, and these great big long starch molecules wouldn't go through. You're the doctor.
Well, I was just wondered if you were going to venture one other suggestion, which was put to me a little while ago, which is that if you eat things that have got a lot of starch in them, they would obviously lodge in your teeth. And if you have this enzyme in your mouth, then it will break those things down, and obviously it will fuel the bacteria in your mouth, but it will break down the starch, and this would help you to swallow stuff more easily. But if that were entirely true, you'd expect to have sort of protein digesting enzymes there too to help break down any meat that gets between your teeth, and that doesn't seem to be the case.
But wouldn't a protein digesting enzyme actually dissolve your mouth as well?
Well, yes, to a certain extent, but then remember that you have protein-digesting enzymes in your guts anyway, because your pancreas makes them, and the guts can tolerate it because they have lots and lots of cells being replaced all the time. It's a good point. It's a good point. I have to bow to that, so you probably caught me out on that one. But Keith in Great Yeldham agrees with you on your observation, Dave. He says, when a piece of white bread is chewed for a long, long time, it begins to taste sweet. This is because enzymes in your saliva break down the carbohydrate molecules into more basic sugars, which can be tasted. And he's gone on to have a go at our teaser this evening, which you've got a few seconds to have a go left at. What gas makes up the majority of the air we breathe? If you want to have a go, 08459 25 2000 is our telephone number. Ken is in Forrington. He says for you guys, Emma and Fraser, is there a lost formula for using water as our main fuel? And do you guys know anything about this?
Well, water itself cannot be a chemical fuel because it is the end product of a very favourable chemical reaction. However, the vast amount of water on this planet, which of course is comprised of hydrogen and oxygen, if it is energised, that is, if we apply primary energy such as solar energy or even nuclear energy, perhaps even nuclear fusion energy in the future, if we apply large amounts of energy to water, we can split it into hydrogen and oxygen. And from this type of reaction may come our salvation in the future when we no longer have any fossil fuels to use.
So you're actually using it as a battery rather than a primary fuel?
Hydrogen is not a primary fuel, but hydrogen is an energy carrier, a storable fuel which can be obtained by energising water with a primary fuel, which of course causes it to split into hydrogen and oxygen.
Here's someone called Simon who's ever optimistic. He says, is the caloric content of food when it's stated on a packet, the amount of energy given off when it's burned, does it take into account how much energy a human can extract from it through digesting it with things like catalysts, in other words, enzymes? And if I were to eat 2 donuts at once, would I take in twice the calories and twice the fat as if I'd just eaten 1? If you eat 10 at once, can you really process them as efficiently as if you just had 1?
The calorie content, which is actually kilocalories, is the energy...
Kilo or
kilocalories?
Could be both.
Kilocalories. This is the energy which would be obtained in an experiment were that food to be burnt in an excess of oxygen.
Got a quick question here, which is about catalysts in the liver, I suspect, because this is about people's sensitivity to alcohol. And it's from Joshua Denton. He says he's from Atlanta, Georgia, likes our show, and says, why is it that some people are very tolerant to alcohol and others only need to get a whiff and they're over the edge? What do you reckon? Can you do that in about 30 seconds?
It has to do with an enzyme called alcohol dehydrogenase, which contains a zinc atom, and different amounts of this enzyme would be expressed in people who have different genetic makeup, and so that is one part of the answer.
So some people can break it down much quicker than others.
Yes.
I think there's one other point to add to that, which is if you are a regular boozer, then you induce the enzymes in the liver to increase the numbers, and so you break these things down a little bit more.
The Naked Scientist Podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Well, that's it for this week. Thank you very much for joining us. On next week's show, we'll be having one of our monthly question and answer bonanzas, a science Q&A show special. An hour of Naked Scientists devoted just to answering your questions. But we do, of course, need some questions. So if you could send in anything, the weirder the better, to chris@nakedscientist.com, or you can post them on the forum of our website, nakedscientist.com/forum. We'll pick them up and we'll try and include them in next week's show. And if you ask a question that's really, really fantastic, we might even give you a prize. In the meantime, don't forget that Naked Science, my book, went on sale recently, and you can get a copy with free delivery in the UK and reduced rate delivery worldwide if you go to nakedscientist.com/book for all the information. Our teaser this evening, we wanted to know which gas makes up most of the air we breathe. The answer was, of course, nitrogen. A big thank you to our guests this evening, Fraser Armstrong and Emma Schofield, and also to Dave Ansell and Anna Lacey and Petro Minch, who helped produce tonight's show. Thanks for joining us, and see you next week.